Fluid flowing through pipe experiences friction at its contact interface with inner wall. The friction dissipates the energy in fluid, and such loss is commonly known as head loss. Darcy-Weisbach equation calculates the head loss based on the flow length, flow velocity, pipe material, and geometry. Generally, rough pipe poses high resistance to the flow and thus causes great head loss. Same effect can be noticed when we are using pipe with small diameter. Fluid that flows with either high velocity or long flow distance is more susceptible to head loss. Let's say we have a 100 meter long mild steel pipe with cement lining. The nominal diameter of pipe is 600 mm. The pipe is designed to convey 7 million liters of water per day. First, let's convert the flow rate from million liter per day to cubic meter per second for unit consistency. The resultant flow rate will be 0.08 cubic meter per second. Then, we will determine the internal diameter of pipe. The pipe wall thickness is 6.3 mm and the cement lining is 13 mm. The external diameter of pipe is 610 mm and therefore, the internal diameter should be 571.4 mm. After that, we determine the flow velocity by dividing the flow rate with cross-sectional area. From calculation, we know the flow velocity is 0.31 meter per second. The friction factor used in Darcy-Weisbach equation can be determined by using Moody diagram. This parameter is dependent of the flow type, Reynolds number, and relative pipe roughness. For mild steel pipe with cement lining, we will use the suggested roughness of 0.1 mm. The relative roughness is calculated by dividing the roughness with pipe diameter, which turns out to be 1.75 times 10 to the power of -4, which might be here. Next, let's calculate our Reynolds number. We may take the dynamic viscosity of water as 0.89 mPa/s, assuming it is in room temperature. Through calculation, the Reynolds number is around 200,000. The flow is transition and the friction factor is 0.0175. Given the following values, we are good to calculate our head loss using Darcy-Weisbach equation. By substituting the values into the equation, we know the loss is estimated to be 0.015 meter head. An alternative way to calculate the head loss is by using Hazen-Williams head loss gradient equation. In this equation, the parameters considered are flow rate, pipe size, and material. Pipe material is represented by Hazen-Williams coefficient, where the smoother the pipe, the greater the value. The pipe size parameter we use here is diameter. The head loss gradient is expressed in the unit of meter head loss per meter flow length. It is high for both small and rough pipe. Moreover, the flow is more susceptible to head loss when the flow rate is high. Let's look at our pipe again. For mild steel pipe with cement lining, the Hazen-Williams coefficient we can use is 100. By substituting the values into this equation, we know the head loss gradient for this pipe is 0.3 mm per meter. Knowing the flow length is 100 meter, total head loss calculated using Hazen-Williams equation will be 0.03 meter. Knowing the pipe material, geometry, and flow hydraulic grade, Hazen-Williams equation can tell us the pipe flow velocity. The pipe material is again represented by Hazen-Williams coefficient. The pipe geometry is represented by hydraulic radius, which is the ratio of flow area and wetted perimeter. For circular pipe under fully pressurized flow, the hydraulic radius can be simplified and equals to pipe diameter over 4. Hydraulic grade is calculated using Hazen-Williams head loss equation, which we discussed earlier. In short, pipe flow velocity is high for smooth pipe, small pipe, and flow with high hydraulic grade. Based on the parameters we used in previous example, we can try to determine the flow velocity using the Hazen-Williams equation. By substituting the Hazen-Williams coefficient, hydraulic radius and hydraulic grade into this equation, we know the velocity is 0.31 meter per second. Barlow's formula is used to determine the maximum pressure a pipe section can sustain. This formula takes pipe geometry and material strength into account. The resistance of pipe is expected to be great if its material is strong or the pipe wall is thick. Sometimes, to use this formula, safety factor is applied to the material strength. Let's look at the steel pipe again. The pipe thickness is 6.3 mm, ignoring the cement lining thickness. The external diameter of pipe is 610 mm, while yield strength of pipe is taken as 275 MPa. By using Barlow's formula, we know the pipe can withstand up to 5.68 MPa of pressure. Joukowsky equation is used to estimate the effect of water hammer in terms of pressure change. This equation works with the assumption where the change in flow velocity is instantaneous, which may be achieved by opening or closing a valve abruptly. The parameters considered are fluid density, expected velocity change, and wave propagation velocity in the fluid. The wave propagation velocity is dependent on fluid density and its bulk modulus. The impact of water hammer is high if the fluid is having high density and wave propagation velocity. It is also critical when we are dealing with huge velocity change. Let's say we shut the valve and stop water flow in the steel pipe in our example. What would be the impact? First, let's determine the wave propagation velocity in water by taking its bulk modulus as 2.1 GPa. Through calculation, the velocity is 1449 meters per second. The flow velocity should change from 0.31 meter per second to 0 if we shut the valve rapidly. Therefore, we take it as negative 0.31 meter per second. By substituting these parameters into the equation, the estimated increase in pressure due to this event is about 0.45 MPa. Now we have seen 5 useful formulas for pipe design. What are the useful formulas you would like to share with us? Tell us in the comment section. Thank you for watching. If you find this video helpful, please share it with your friends. We will see you guys soon. Goodbye.